Today we're going to talk about two concepts that both include the word percent, but are not exactly the same thing. So the first one is going to be mass percent, and later we'll talk about percent yield and what the difference is between these. But let's start with mass percent. So what exactly is it? It's also known as the percent composition, and the key is that this is the fraction of an element and the mass of that element within a larger compound. You just take that fraction and you multiply by 100, and that gives you the mass percent. So it's a pretty simple concept. So why don't we look at the first example here? What is the mass percent of oxygen in water? And you can see that the atom oxygen is going to be O, water is H2O. So there's only one oxygen within water, and we just have to take into account what the molar mass of oxygen is. If you look at the periodic table, you'll see oxygen has a molar mass of 16 grams per mole. And if we follow the equation that we had earlier and we divide by the molar mass of the compound, well, when you add the additional two hydrogens to oxygen, that gives us a molar mass of 18 grams per mole. You should get familiar with the molar mass of water. You'll notice that 18 grams per mole is a very common molar mass you'll have to use. If you're going to divide these two numbers, well, if you don't have a calculator, what would be the easiest way of going about it? You can look at 16 and 8, and we can simplify that by dividing by 2. So you'll have 8 over 9. And 8 over 9 should be approximately 90%. So for the sake of the test, doing this type of calculation, even approximately is good enough. Let's move on to the next example, which is a little bit more difficult. What is the mass percent of nitrogen in ammonium nitrate? So now the difficulty has gone up specifically because the compound that we're looking at includes nitrogen in two different places. One is going to be in the ammonium, and the other one is going to be in the nitrate. So we have to take into account the fact that there are two nitrogen atoms within this larger compound. And so where do we start? Well, we're going to need the molar mass of nitrogen. So if we look at the periodic table, we'll see that the molar mass of nitrogen is approximately 14 grams per mole. And if we have two of those atoms, then we'll start by saying that there is 28 grams of nitrogen. We just use the typical molar mass for this type of question. But then we have to take into account the remaining atoms that we have here. So we have hydrogen as well, and we also have oxygen, and we'll take those into account in a similar fashion. So we'll go ahead and sum all of that up. And when you take 28 and 48 and you add those together, then you should get 76. If you add 4 to that, then you will get 80 grams per mole of ammonium nitrate, and that's for the entire compound. So all we have to do is we take our 28, which was what we had found as the mass of nitrogen, and we are going to divide that by 80. And similarly, we'll multiply that decimal by 100. And so what would be the easiest way of going about this? Well, you can consider this as 28 over 80 if you'd like to. You can consider this as 14 over 40. You can also do 7 over 20, however you'd like to do it. So I'm going to simplify this to 7 over 20, assuming we divide each of those numbers by 4. And then if you're not sure of how to do this, instead of going directly into doing long division, it might be smarter to just change the scientific notation of the numerator, specifically 7 here. So maybe it'd be easier if we change 7 to 70. And what we'll do is we'll say 70 times 10 to the negative 1, because that's the same thing as 7. And then you can continue to divide that by 20. And we'll rewrite the 100 that we were going to multiply by as 10 to the 2. So now we have scientific notation form of this. And 70 divided by 20, so 20 goes into 63 times, and it'd go into 70 3.5 times. So we can say 3.5, and then we can multiply our 10 to the negative 1 and our 10 squared, and then that will give us 10. Because ultimately what we're doing is we're adding negative 1 and 2 since we're multiplying these scientific notations together. So what's 3.5 times 10? That is equal to 35. So this is going to be 35% nitrogen within the ammonium nitrate compound. So I hope that this was helpful in explaining how mass percent works. And ultimately on the test, maybe you'll get one question like this, but it's worth it when it comes down to it to know how to do it. So let's move on to the next topic. And this one is going to be percent yield. So mass percent was about how much of a certain element in mass was within a larger compound, but percent yield is a completely different idea. And the concept that it relates to is the difference or the ratio between the actual yield and the theoretical yield, which if you remember from my stoichiometry video, we talked about how you can use a balanced equation to theoretically predict how much product should form. But we know that in real life, there's an actual yield that occurs, and it tends to be, if not always, is less than the theoretical yield. So therefore, we can take that decimal, knowing that the actual yield is likely some percentage of the theoretical yield, and we can see how efficiently the reaction occurred. And so the formula for that is pretty simple. You just take the actual yield and divide by the theoretical yield and multiply by 100. So yet again, it's finding a percent, but the amount yield that actually physically occurred. So why don't we move on to the example for that? And here the question is, you react 10 grams of hydrogen gas with excess oxygen to produce water. You collect 80 grams of water. What is the percent yield? So if you remember from our stoichiometry video that we're going to have to use the balanced reaction for the conversion of hydrogen gas and oxygen into water. So what is the balanced equation? Well, first things first, hydrogen gas should be H2. Oxygen gas is O2 because both of those are diatomic. And then we'll form H2O, which we all should be familiar with. So let's go ahead and balance this. I see there's two H's on both sides, but there's two oxygens on the left and only one on the right for the product. So what do we have to do? Well, by default, we're going to have to throw a 2 in front of H2O. What does that cause us to do? We have to go back to the reactant side, and we have to balance the H's. So now that we have 4 H's as the product side, then I need 4 H's on the reactant side. Therefore, we put the coefficient of 2 in front of that. If you remember from the stoichiometry video, then this should be easy. If you haven't watched the stoichiometry video yet, please go back and watch that first. So now that we're going to figure out what the limiting reactant is, or barely have to figure it out because the question is telling us that there are 10 grams of hydrogen gas given in excess oxygen. So clearly our limiting reactant is going to be the hydrogen. So the first thing you would have to do is determine how many moles is that. Let's say 10 grams of hydrogen gas. And remember, hydrogen gas is H2. So therefore, we have to divide that by the molar mass of H2, which each hydrogen is 1. Therefore, the molar mass of H2 is 2 grams per mole. And so this gives us 5 moles of H2. So if we do a little bit of stoichiometry, we know that the mole ratio between H2 and water is 1 to 1 or 2 to 2, but consider that 1 to 1 simplified. So since that's the case, that means that if I'm starting with my limiting reactant of 10 grams of hydrogen gas, and that's 5 moles of H2, then equally, that will also be 5 moles of H2O because 1 to 1, 2 to 2, 3 to 3, it doesn't matter. It's just 1 to 1 if you simplify. Therefore, however many moles of H2 we start with, we would get the same amount of moles of water. We would need half as much oxygen, but the question already told us that it's in excess, so that doesn't really matter. We'll just have a surplus of oxygen left over, unreacted. So if we know that we're going to end up with 5 moles of water, then all you need to do is multiply that 5 moles by the molar mass of water, which as we discussed earlier is 18 grams per mole. And we'll simply take our 18 and multiply by 5. In this case, I'm not going to approximate because I want the theoretical yield to be exact. So we'll just do some simple multiplication. We'll say this is 0, 4. So ultimately, this shows up as 90 grams of water. If you remember our equation from before, what do we have to do? We have to take our actual yield, which was given by the question, which is 80 grams, and divide by 90 grams. And I'll give you a little tip here. Anything divided by 9, so let's say 80 divided by 90 is the same thing as 8 over 9. Anything divided by 9, if you take the numerator and then you repeat it, so let's say 0.888 repeating, but I'll just write 0.88, is going to be the result of that fraction. So if it was 1 over 9, it would be 0.111, 2 over 9, 0.222, 3 over 9, 0.333, so on and so forth. So 8 over 9 is 0.88. You can call that 88% or 89%. You can round it to 90% on the test. It's probably not going to be that big of a deal. I don't think they'll give you that much of a hard time in terms of the options you'll have to choose from. And this could be very useful for you to know that there is an 89, let's say, all around, percent yield of water that we got from the reaction in comparison to the theoretical yield of 90 grams. We only got 80 grams. So I hope that this was useful in explaining the difference between these and how they're applied on the test. Thank you for watching and hopefully see you again soon.